Hi, and welcome to our conversation about universal gravity continued. So, Newton was the guy who came up with this idea, and we have all heard the fictitious story about the apple falling out of the tree and hitting him on his head. But I think it was through his contemplation of how things orbit one another and how everything seems to be going in circles that he came to the realization that he thought that actually everything with mass would attract everything else with mass. And the law that he came up with, or Newton's law of universal gravitation, and then I wrote myself a little note to not forget to talk about altitude. I'm going to have to change my pen size here. Is relatively straightforward. Fg, and we'll talk about it in a second, G m1 m2 divided by r squared, where Fg is just the force due to gravity. It's due to gravity, and that little subscript G just tells us, reminds us that the force we're actually talking about is in fact gravity. And this is measured in something called newtons, which is just abbreviated with an N. So again, as we alluded to in the previous lesson, we are going to talk about a bunch of different forces. And this particular one, Fg, is the force due to gravity. And we'll give each one its own unique subscript so that we all know what we're talking about. I'm going to skip big G for a second, and I just want to talk about M1 and M2. M1 and M2 are any two masses. Any two masses at all. This again could be the Earth and the Moon. It could be the Earth and the Sun. It could be Mars and the Sun, because all of those things we think about regularly with gravity. It could also be, though, a person being attracted to the Earth would also be a force due to gravity. And since two people have masses, there would also be a gravitational force of attraction between two people. So any two masses will have a gravitational force of attraction between the two. Of course, masses are measured in kilograms, and R is the separation of their center of masses. And this is where I'm going to come back and I'm going to talk in a second about altitude. Human beings are relatively small. Our center of masses are right around our belly button. But when we start to talk about planets, they're huge. And then we have to talk about whether that distance from their center of mass, which is at the dead center, to the outside where things might actually be, is an important conversation to have. G is just a constant. It is the universal gravitation or gravity constant. So this constant works anywhere in the entire universe as far as we know, and its value is 6.67 times 10 to the negative 11. I am running out of space, so I'm just going to do a little air. Well, actually, I can probably just get fancy and we can maybe just move some things around, and I can make the space that I need. We can drag this down. Yeah, there we go. We can put those brackets back there, and I can erase that. So when we talk about units, so units work the exact same way as numbers. So if I take this expression and I rearrange it for G, what I would do, and I'm going to draw this in red and then I'm going to erase it afterwards so that people can see what I'm doing, I would multiply both sides by r squared divided by m1 m2. I can multiply this side by r squared divided by m1 m2, and that would mean that my R cancels with R, and my M1 cancels with M1, and my M2 cancels with M2. And I think I messed up my 1s and 2s there, but you get the idea. So then I'm left with R squared FG over M1, M2 would be equal to big G. And now I'm going to go back and erase these so that afterwards they're still legible. And switch back to my blue color. Man, is G. So when I look at my units for this one are a little bit weird. My units is going to be, I've got force on the top, so I'm going to need newtons, because my left-hand side of my equation is going to have to equal my right-hand side of the equation. So my units are going to be newtons. R is going to be in meters, which we didn't talk about. I'll put it down there too. Meters. And it's meters squared, or it's distance squared, so it's going to be meters squared, divided by my mass 1 and mass 2. Both of those are in kilograms, so kilograms times kilograms is kilograms squared. And so that constant really just makes this equation work. Again, this equation was kind of determined experimentally by Newton, and he didn't know why it worked. He didn't really have an understanding of why gravity worked this way, but it does work to calculate the magnitudes of the forces, and that's why we kind of end up with this really obscure constant, 6.67 times 10 to the negative 11. So when we talk about center of masses, if I talk about things like planets, where to scale, this is Earth, and this still isn't to scale, that's the sun. Notice how the distance from the outside of the sun to the inside of the sun, compared to this whole distance, is very small. And where we can get this value, if this is Earth, and this is the sun, is all we have to do is we can look at our equation sheet. So I've got one up here. This one should look like the one that you've got. And right on my equation sheet right here, it says radius of orbit around sun, 1.5 times 10 to the 11. So if I go back here, this is 1.5 times 10 to the 11 meters. And that is to the center of mass. However, and I'm running out of space here, if we talk about altitude, and if you want to talk about, so here's the Earth, and then we want to talk about maybe a satellite, and there's a satellite with some solar panels off the outside. If we talk about altitude, and let's call this, I don't know what a satellite's at, let's call it 10,000 meters. It turns out that the radius of the Earth, if I go back to my handy-dandy formula sheet, my radius of the Earth is 6.38 times 10 to the 6. 8 times 10 to the 6 meters. And now this is important. So the distance from the center of mass all the way out to my satellite, my radius here would need to be 6.38 times 10 to the 6 plus that 10,000 meters. So let's look at a couple of examples. Gravity example number 1. What is the force of gravity or gravitational attraction between the Earth and the Moon? So we're going to have to look a couple of things up. We're going to have to go to our formula sheet, and we're going to have to look up what is how far apart they are. We're going to have to look up the mass of the Earth and the mass of the Moon. I can jump over to my formula sheet, and it's all on here. Definitely don't need to memorize it. I have the mass of the Earth right here, 5.98 times 10 to the 24. I have the mass of the Moon, 7.35 times 10 to the 22. And we're given a couple of radiuses here. So the radius of the Moon and the radius of the orbit around Earth. We want how far apart the Earth and Moon are, so we're going to use this one, the radius of orbit around Earth, this 3.84 times 10 to the 8. And I think if I go back here, that's actually what I've got covered. The mass of the Earth, the mass of the Moon, and how far apart those two things are. So if we set up our equation, Fg is equal to gm1 m2 divided by r squared. Our Fg is then 6.67 times 10 to the negative 11 times my mass. One of my masses is 5.98 times 10 to the 24. And I'm running out of space again. So I'm going to move that over. 7.35 times 10 to the 22, all divided by this 3.84 times 10 to the 8. And do not forget to square that. So you notice how this is relatively straightforward. All I had to do was pick a couple of numbers from the formula sheet, put them in appropriate places in the equation, and then calculate them. But notice how big the numbers are and the probability of a simple mistake keying it into your calculator. So take your time with these and make sure they're plugged in properly, and maybe double check your work. I think if I scroll down here, what I've got at the bottom is Fg is equal to 1.99 times 10 to the 20 newtons. And I might as well move that back up so it can live with the rest of the solution there. Cool. Gravity example number 2. What is the force of gravity between an airplane flying at an altitude of 1,000 meters and Earth? So again, we're going to need to have to figure out 3 things. We're going to need to know the mass of the 2 objects, which is Earth and the airplane, and we're going to need to find out how far apart their centers of mass are. Anytime I see this word altitude, I should be thinking in my head, I'm going to have to find the radius of a planet and add it in there somehow, and we'll talk about how to do that now. I did a quick Google search, and I found that a Boeing jet is about 80,000 kilograms. And then if we go to our formula sheet again and pull off the mass of Earth and the radius of Earth, we get these guys. Mass of Earth and the radius of Earth. So again, if we have our Earth, and then this is going to be a really bad plane, so I'm just going to draw a little dot, and then if we're wondering what it is, I'll just write plane above it. We can see that from the center of Earth, which is 6.38 times 10 to the 6 meters. To the plane, this radius doesn't quite get there, and neither does this one, which is 1,000 meters. So we're going to have to add those together to get the radius. Our radial separation, which is r, is 6.38 times 10 to the 6 plus that 1,000. You don't have to do it as a separate calculation. We're just going to have to remember to square it when we do it. So when I'm looking at my force due to gravity equation, my gm1 m2 divided by r squared, that's what's going to have to go in there. Fg is equal to 6.67 times 10 to the negative 11 times one of my masses. Let's do Earth's, 5.9. 8 times 10 to the 24 times the other one, which is 8,000. You can either type that in, 80,000, sorry. You either type that in scientific notation or not, that's up to you, divided by this 6.38 times 10 to the 6 plus the 1,000 meters of altitude. And do not forget to square that. Again, I think if we scroll down, I can pick up this solution. And I got earlier that this was 7.84 times 10 to the 5. Don't be afraid to double check my math. If you've been in my class, you know I make mistakes. Cool. And that's how an example with altitude could work. This one is fairly straightforward. What is the force of gravity between the Earth and a person on the surface? We're going to assume our person on the surface is 70 kilograms, which is a smaller person. We look on our formula sheet, we find the mass of Earth, we know the mass of the person, the radius of Earth. I'm not going to type these in just because I think they're really straightforward, but I would like to draw your attention to this solution. If you do plug it in, give it a go on your own. I'm going to move this up. The force of gravity will be 686 newtons. The next one I would like to do, though, and what I would like to do is I'd like to compare this 686 newtons with what we get in this next one. So we talked about this already. What is the force of attraction between two people? We don't feel this. I never feel like if I get too close to someone, I get pushed towards them, unless, I particularly like them independent of it. But I don't normally feel that. We don't go walking down the sidewalk and sway into one another unless we're being a little bit silly. So I've got my two masses, which is M1, 70 kilograms, M2, 70 kilograms, and they're 2 meters apart, because we're not supposed to get closer than 2 meters to each other right now, so we're going to stay our 2 meters apart, which means if we plug this into our equation, Fg is gm1 m2 over r squared, so my Fg is going to be our 6.67 times 10 to the negative 11 times 70 times 70 divided by 2 squared. That's a horrible squared. I'll try that again. I'm starting to rush a little bit. I'm worried about my battery. I got a battery signal. And what I get is that Fg is equal to 8.17 times 10 to the negative 8. So we notice between this solution, 8.17 times 10 to the negative 8, which is a very, very small number, and this solution, which is the force between somebody and the Earth. Notice how this one is 686 newtons. We would feel this. We feel this all the time. This is what keeps us stuck to the Earth. But this force is so small that we can't perceive it at all. However, if we were stuck out in space, and we were 2 meters away from another human, and we didn't move at all, or we didn't throw anything, is actually about the only way this would work, you would end up slowly accelerating towards each other. You would feel that force. Now, this is when we talk about things like the start of the universe, how the universe started. You just have a big cloud of dust, huge cloud of dust, and all of those very small gravitational forces between all those pieces of dust is what ends up pulling an entire solar system together. While before solar systems, you get galaxies forming, and then you get clusters of galaxies, and all sorts of very cool superstructures in the universe that come out of all of these really incredibly small gravitational forces. And that's about it for gravity. Hope you guys are having a great day.